per se here, because that stream is coming in, stream 1 is coming in, stream 2 is coming in, stream 3 is going out, stream 4 is going out. So it is not it's not an isolated system per se now. It is a
So
system
if
in which
we
things are coming in, going out all the time.
or rather I said that the heat taken is equal to the heat given.
Okay,
That's how
that's
it
fine.
is.
That's fine. That's fine. That's fine. So you are saying heat lost by hot air and heat gained by the solids and water, they are equal.
Yes, sir. So one more doubt.
Yeah.
Uh, for the latent heat of water
Hmm.
above 100, would it be less than 540?
Yes.
Okay.
See, at 100 degrees centigrade, latent heat is 540 kilocalories per kg. If you go to higher and higher temperatures, 120, 130, 140, you go all the way up to critical temperature and critical pressure. What is the latent heat at critical temperature and pressure?
I'm not sure, sir.
What does the critical temperature and pressure mean?
Above which it cannot be liquefied.
Above which it cannot be liquefied is one answer, but if you start looking at the properties of the vapor and properties of the liquid, they start approaching each other, like density, viscosity, right? So if
Okay.
they're becoming like each other, that means they are becoming indistinguishable. If they are becoming indistinguishable, latent heat will become zero.
Okay. Understood, sir.
Yeah. Okay. Okay. So now whether okay, recording has started. That's fine. All right. So shall we see this problem? Shall we solve this problem, or shall we go to the next problem, or shall we solve the problem with sort of with respect to that reference method?
Yes, sir.
Yes, sir.
Yes means what? Yes for what?
With the reference
To
method.
solve the method with the reference method.
Okay. 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 Fine. 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 We will solve. Okay. So let me just delete all these things, because I'm not going to tell you the actual. I'm not going to solve it in the sense that completely we will solve and get to the values. I'm just going to show you how to solve and just show you in terms of the formulae, and then you can actually substitute the values, and uh, we will calculate. You can calculate. Let me just drag and delete all this once and for all. All right. Okay. So what we are going to do, like potential energy, we will say that enthalpy at some reference condition is zero. Like we are saying, potential energy at the ground floor is zero, right? But if there is a basement, then we can say that even the potential energy, if I set basement as a reference zero and potential energy, then even the ground floor will have some substance at the ground floor will also have some potential energy. Or if I'm living on third floor, if I say the floor of my house is a reference, then any object on the floor of my house has zero enthalpy, right? So we are going to say that at some reference condition, we are going to say enthalpy is zero. Now, for setting enthalpy to be zero, we have to specify components and their state. So what components are there in this problem? In this problem, there is a component P that is in the solid state, right? P is not in the vapor state. P is not in the liquid state. P is our crystals or something like that. We have air, the dry air part of it. Dry air is in a gas state, vapor state, if you like. Okay. We also have water. Now, water is in the liquid state as well as vapor state, right? In the stream 1 and stream 3, water is in the liquid state. Stream 2, there is no water vapor. Stream 4, water is in the vapor state, right? So obviously I have to specify zero enthalpy for all the substances, but in any particular state, right? Obviously liquid water and water vapor cannot have the same zero enthalpy, because in order to make it vapor, I have to supply enthalpy, latent heat of vaporization. So I will just say that either liquid or vapor. Let me just say in this particular case, liquid, in the water in the liquid state, these components and these states, they have zero enthalpy at a temperature of whatever is my choice. I can say 5 degrees, I can say 25 degrees, I can say 0 minus 273 degrees centigrade. I can say temperature of the sun 5000 degrees centigrade. I can say temperature of the black hole 1 million degrees centigrade. Whatever is my choice, I will make the enthalpy of these components at this particular temperature and say that they have zero enthalpy. Just like potential energy, we can take reference as third floor, second floor, first floor, ground floor, basement, center of the earth, whatever we like. Okay, so just for this particular problem, I'm just going to say that enthalpy of these components in these particular states, that means P in the solid state at 30 degrees centigrade has zero enthalpy, dry air in the gas state has zero enthalpy, water in the liquid state has zero enthalpy. The advantage of doing this 30 degrees centigrade is that if you look at stream 1, so stream 1 contains P in the solid form and water in the liquid form, and these are at 30 degrees centigrade, isn't it? Stream 1. Okay, so I will say that the enthalpy of this stream, because these are at the reference condition, is 0. Do you agree? Yes, no?
Yes, sir.
Yes, sir.
Yes, sir.
Now let's look at stream 2. What does stream 2 contain? It contains dry air at what temperature? 200 degrees centigrade. 200 degrees centigrade. So if I think in terms of enthalpy versus temperature graph, I have set that for dry air, 30 degrees centigrade has zero enthalpy. Okay. I have air actually at 200 degrees centigrade, right? So the enthalpy change, if I find out enthalpy change for this process, let's say process 1, black arrow, what is the enthalpy change for this process is mass of air, mass flow rate of air, Cp of air into 200 minus 30. Right? So mass flow rate of air is 100,000 kgs per hour. 100,000 kgs per hour. Suppose I say Cp is 0.24 kilocalories per kg Kelvin, and temperature change is 170 Kelvin change. Right? So kgs will go away, Kelvin will go away. This will be so many kilocalories per hour. This is the enthalpy change. You can actually calculate. I don't want to calculate. You can calculate. This is the enthalpy change in taking air from 30 degrees centigrade, the reference condition, to the actual conditions of stream 2, isn't it? And what is the enthalpy change for process for this process 1? This is nothing but enthalpy of air at 200 degrees centigrade, dry air, minus enthalpy of air at reference conditions, right? This is 0. So enthalpy of stream number 2 coming in to this control volume due to stream 2 from stream 2 is so many kilocalories per hour. Do you agree? What we are taking is this control volume. This is our control volume, the dryer. Okay. Is that okay? Everybody comfortable? Okay, yeah.
Yes.
Now let's look at stream number 3. What does stream number 3 contain? Stream number 3 contains so many kgs per hour of P and so many kg per hour of water in the liquid state, right? You can calculate. Everybody can calculate by material balance. It seems like a childish problem now. We had calculated this so long ago. If it is 30,000 kgs per hour total, 80% is P. That means this is 24,000 kgs per hour and this is 6,000 kgs per hour in stream number 1. So P in this stream number 3 would be 24,000 kgs per hour. And water is 1%, P is 99%. So water would be 24,000 into 1 divided by 99. That is nothing but 242.42 kgs per hour. Anybody gets this value? Anybody doesn't get this value?
Same, sir.
Yes.
Just 242.
Yeah, 242. Right, now let's work out enthalpy of stream number 3. What does stream number 3 contain? Stream number 3 contains P, 24,000 kgs per hour in the solid form at what temperature? 40 degrees centigrade. 40 degrees centigrade. 40 degrees centigrade. It also contains water, 242.42 kg per hour in the liquid state at 40 degrees centigrade. Okay. So enthalpy of this stream number 3 with respect to this reference, can you tell me now? That would just be 24,000 into Cp of solids into 40 minus 30 plus 242.42 kg per hour into Cp of liquid water into 40 minus 30 enthalpy with respect to the reference. So this is in terms of kgs per hour. Cp is in terms of kilocalories per kg Kelvin. Temperature change Kelvin. Kelvin cancels, kg cancels. So this stream number 3 is taking out enthalpy at the rate so many kilocalories per hour. Do you agree? Can we go forward?
Yes, sir.
Yes. Now, let's look at stream number 4. What does stream number 4 contain? It is going to contain 100,000 kgs per hour of dry air. Right? Dry air is not changing. How much water vapor it is going to contain? How much water vapor it is going to contain? If I do material balance across this control volume, blue control volume, how much water it will contain?
5757.57.
Right. 6,000 minus 242.42 kg per hour of water vapor. Right. So if you just calculate this number, 6,000 minus 242.42. It is 5757.58, let's say. Okay. Now, what is the temperature? That we don't know what this temperature is, right? But we know that it contains this many amount of dry air and this much amount of water vapor. So what we are going to find for stream number 4, right? What does stream number 4 contain? Dry air, 100,000 kgs per hour. Oops. At some temperature T degrees centigrade. We don't know that T, right? What does it contain? It contains water vapor at the rate 5757.58, right? 5757.58 kg per hour at T degrees centigrade, isn't it? What is my reference? My reference is dry air at 30 degrees centigrade having zero enthalpy, and liquid water at 30 degrees centigrade having zero enthalpy. So with respect to this reference, if I look at the enthalpy of this particular stream, what would that be? Enthalpy of stream number 4 would be enthalpy associated with the dry air and enthalpy associated with the water vapor. What is the enthalpy associated with the dry air? It is at 100,000 kgs per hour mass flow rate into Cp 0.24 kilocalories per kg Kelvin into temperature that is unknown T minus 30 kg per hour kilocalories per kg Kelvin. Okay. So this is in terms of kilocalories per hour. Do you agree for the air part in stream number 4?
Yes,
Yes,
sir.
Yes. Now water vapor. Water is in the vapor state, right? Whereas in the reference condition, it is at the liquid state. So be careful. If we look at the water part, again, I am drawing a graph of temperature versus enthalpy. Look at only the water vapor part. 30 degrees centigrade, zero enthalpy. This is liquid water. What is there in actually in stream number 4? It is at T degrees centigrade. It is in the vapor state. All right. So I need to go from here to here. I need to find out the enthalpy change, right? I can do it in different ways. Rather than doing it this way, I will say I will go by this path, the red path. I will vaporize water at 30 degrees centigrade and then heat up water vapor to T degrees centigrade. That would be the enthalpy change. Or I would heat the liquid water to T degrees centigrade and then vaporize liquid water to water vapor at T degrees centigrade. Or I don't want to know what that T is. I will take it up to 100 degrees centigrade. I will heat up liquid water to 100 degrees centigrade. I will vaporize liquid water at 100 degrees centigrade and I will cool water vapor from 100 degrees centigrade to T degrees centigrade. I can take this red route 1. I can take route 2. I can take route 3. All these three will give the same answer because enthalpy is a state function. It is going to depend only on the endpoints. Like if you are climbing a mountain, no matter what route you take to climb the mountain, the change in height, change in potential energy when you reach the top of the mountain is still the same. What is the ground floor minus the, or what is the height of the mountain minus the base of the mountain, right? That's the potential energy change, state function. Of course, how much energy you have spent, whether you have, how much energy you have spent in walking, that's different, right? But that's not what we are worried about here. We are worried about enthalpy change here. Okay, do you agree? So if I take the route 1, enthalpy associated with this water vapor would be, I have to vaporize at 30 degrees centigrade and heat up water vapor from 30 degrees centigrade to T degrees centigrade. Right, this is our route 1. So what is vaporization? So 5757.58 kg per hour multiplied by lambda at 30 degrees centigrade, plus now water vapor, it is already in the vapor state, 5757.58 kg per hour into Cp of water vapor into T minus 30. Right, if I take route 2, it is 5757.58 kg per hour. I have to heat up liquid water, Cp of liquid water into T minus 30 plus 5757.58 kg per hour into latent heat at T degrees centigrade. Right, route 2. If I take route 3, it should be thicker. I don't know why it is not thicker. It is thicker here. Route 3, if I take, that's too thick. Route 3, if I take, I have to heat up liquid water, 5757.58 kg per hour into Cp of liquid water into 100 minus 30 plus 5757.58 into lambda at 100 degrees centigrade plus 5757.58 into Cp of water vapor. Now it is to be cooled from 100 to T degrees centigrade. Right, route 3. Do you agree? Any route we can take, answer will come to be the same. Homework is you take these routes and make sure that they are the same. So let me just take route 1 just for simplicity. So enthalpy associated with stream 4 now. With respect to our reference that we have defined, it is enthalpy for the air, that is this part, 100,000 into 0.24 into T minus 30, and enthalpy of water, I am just taking route 1, so that is 5757.58 kg per hour into lambda at 30 degrees centigrade plus 5757.58 into Cp of water vapor into T minus 30. Right, this is the enthalpy associated with stream 4. It is also in terms of kilocalories per hour. Just make sure that the units are the same. Now if I take this whole dryer as a control volume, this our blue control volume, right, if you take this blue as a control volume, now we can say enthalpy balance, just like we have been saying material balance, whatever enthalpy comes in, right, why this weird color, enthalpy coming in must be equal to enthalpy going out. Why? Because there is no extra enthalpy that we have provided to the dryer, or there is no heat lost from the dryer. We have made it nice insulated adiabatic kind of dryer. No heat comes in from outside, no heat is lost to the surroundings. Right? So enthalpy coming in. So enthalpy coming in from stream 1 plus enthalpy coming in from stream 2 must be equal to enthalpy going out in stream 3 plus enthalpy going out in stream 4. Right? Do we have everything? Yes. we have enthalpy of stream 1, 0 kilocalories per hour. We have enthalpy of stream 2, so many kilocalories per hour we worked out. We have enthalpy of stream 3, that we worked out. And we have now enthalpy of stream 4. Right? Only one unknown is there. You just solve for T. Right? Is that okay? Is it okay now with respect to reference? Any other question? Any other doubt? Anybody has any doubt in this method? Yes, no?
No, sir.
Ansh doesn't have doubt.
No, sir. No, sir.
Can we go to the next problem?
Yes, sir.
Yes,
Yes,
sir.
sir. Yes, sir.
Yes, sir.
Okay. So there is something called as cooling tower. In chemical plants. I will tell you what that is. So have you, so at home, if you have to cool something, what do you do?
Put it in the fridge.
Put it in the fridge, okay. Um,
Or increase its surface area if it's a
okay,
liquid.
okay. Suppose you are eating Maggie, you have made Maggie and you want to eat Maggie, it is just boiling hot. Now, how do you cool Maggie?
We take a plate and
Take it in a plate, all right, and do what?
and spread it like
Spread it out, yes, and do what?
Keep it
Stir it under the fan. Stir it.
Keep,
Place it under the fan.
stir it and keep it under the fan, right? There's some other way also you can do.
Sir,
Is to
take a
use-
bigger utensil and then put water in it.
Right. You take your Maggie here and your spoon, and you take water in an outside container and make sure that you stir this also, right? So this water picks up the heat from Maggie, right? And this water becomes hot. Now, what do you do with this water? The Maggie, of course, you eat, right? So that is out of question. What to do with Maggie is understood. What do you do with this hot water now? Give it to your mother. Give it to your parents. Give it to your younger sister or younger brother. No? What do you do with this hot water at home? Just throw it down the
pour
drain.
it down the sink.
Throw it down the sink, right? Unfortunately, when you're talking about plants, you use the same concept. You use something called as cooling water to take out heat from something. Let's say you want to condense some vapors, or you want to cool something from, let's say, 200 degrees centigrade to some 40 degrees centigrade or something like that, 50 degrees centigrade. You use something, you use the cooling water to take out heat from that particular process or substance. And in turn, this cooling water gets heated. Let's say it gets heated to, let me just tell you the problem so that we know the exact values. Let's say it gets heated to 50 degrees centigrade. Okay. Now, what do you do with this cooling water that has now become hot in the process? If you throw it down the gutter, what will happen?
So we'll have adverse effects in the environment due to heated water. The overall temperature would rise.
ग्लोबल वार्मिंग वो तो बहुत दूर का चीज है. ग्लोबल वार्मिंग तो उससे
So
नहीं होता है.
not global warming, but
हाँ
the regional waters would get heated up, and that would not be good.
हाँ 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 हाँ. Who will create a problem? Who will protest?
Fishermen.
So you see, suppose you have a plant. Suppose there is a sea and you have a plant here. Now, if you throw this cooling water down into the sea at 50 degrees centigrade, there are some nice looking creatures here which are swimming. So these people will have problem. These creatures will have a problem, right? So it is a pollution. Now, have you heard of this place?
No, sir.
Never heard of this place.
No, sir.
It was in the news for some reasons about a year or 2 years ago. Never heard of it.
I've heard about the plant, that it is a nuclear plant.
So there was a nuclear plant at this location, and this nuclear plant was taking seawater for cooling, and this seawater was being sent back into the sea, and then these fishermen started protesting because it will have adversely affect their the fish there, and therefore their livelihood will be at stake, right? So seawater, maybe it is coming into the plant at 30 degrees centigrade, and it was going out maybe at 40 or 45 degrees centigrade. Just for this problem, we are taking 50 degrees centigrade. So then these fishermen started protesting, and therefore this nuclear power plant was ended up in some problem, but it is resolved now. It is on. So we need a way to cool the water from, let's say, 50 degrees centigrade to some, let's say, 30 degrees centigrade, so that the cooling water can be recycled back to plant, right? So what we will do is, this was our, let's say, sea, this was our plant. We will take cooling water, sea water, 30 degrees centigrade. We will get hot water. This is at 50 degrees centigrade, but we will do something to this water so that we can recycle cooling water at 30 degrees centigrade. Then I don't need this. I'll need it, some amount I will need, but not large amounts I will need. Do you agree? So that something is done in something called as cooling tower. So cooling tower will be used to cool that hot water back from 50 degrees centigrade to, let's say, 30 degrees centigrade, and we will recycle that cooling water back into the plant, right? Have you understood the problem, or have you understood the context of the problem? Now I will tell you the actual problem. Yes, no? Context of the problem is clear?
Yes, sir.
So this device called as cooling tower, it's an equipment okay. So this hot water, now this is the actual problem that we are going to solve. Let's say this hot cooling water is at 50 degrees centigrade. We spray this cooling water and make it flow down this column. It's a column, and then we collect this cooling water. So that means heat has to be taken out from this cooling water, from this hot water, right?
Yes, sir.
Can you think of some way of taking out heat from this cooling water at 50 degrees centigrade?
So supplying air that is at a lower temperature
Okay. So one
and
we have,
very less humidity. Relative
right,
humidity is very low.
right, right. So we supply air, ambient air, which is at a temperature lower than 50 degrees centigrade. Also, it is not 100% saturated. So some of the water vaporizes to take care of that saturating the air, and then the rest of the water gets cooled because enthalpy is taken out from the water itself. Just like our cooling, we had wet bulb temperature. Do you recall? That water was cooling down. Do you recall that? Do you recall the wet bulb temperature? We had water temperature falling, 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 falling. Then it came to wet bulb temperature. Yes or no?
Yes, sir.
Same thing is going to happen here as well. Right? So we will supply ambient air, which is at a lower temperature. This air will now become hotter and more humid air. And that this air can go to atmosphere. Right? Do you agree with this? This is how a cooling tower will work. And then this cooler water we can recycle. Okay, so here is the problem. So assume that this hot cooling water is at 50 degrees centigrade. We want to have this cooling water after passing through the cooling tower. We want it to be at 35 degrees centigrade, so we can recycle it back to the plant. Air that is supplied, ambient air, let's say it is at a temperature of 30 degrees centigrade. It has a wet bulb temperature of 25 degrees centigrade. Okay, let's take the basis that we are supplying 1 kg of this hot cooling water. Okay, and we supply 0.5 kgs of dry air. Dry air means the dry air part of the ambient air is 0.5 kgs, but it will also come along with water vapor because it has a wet bulb temperature of 25 degrees centigrade. Okay, let's assume that the total pressure is 760 mm Hg throughout. Okay, everybody can visualize the problem. Hot water, 50 degrees centigrade, flows down this column. Ambient air comes in contact with it at 30 degrees centigrade, wet bulb temperature at 25 degrees centigrade. It contains 0.5 kgs of the dry air plus the water vapor. The hot cooling water loses heat and air gets humidified. So the air going out will be at a higher temperature than 30 degrees centigrade. Air going out will be more humid than the incoming humidity of the ambient air. And the water, which was at 50 degrees centigrade, in turn gets cooled. We want it to be at 35 degrees centigrade. Do you can everybody visualize the problem? Yes, no?
Yes, sir.
Yes.
Yes, sir.
Okay. Here is what I want you to find. I want you to find right. Let's assume that this humid air this hot humid air becomes 100% saturated. Okay. but it is at a higher temperature than this T degrees centigrade. It is at a higher temperature than this 30 degrees centigrade. So let's say it is at T degrees centigrade. This is what I need to find out. And I need to find out how many kgs of this cooling water, which is at 35 degrees centigrade, we will get, because some of the water, 1 kg that we have supplied, part of it will get vaporized. So we will get something less than 1 kg here in the cooler cooling water at 35 degrees centigrade. Do you agree? So these are the two things that I need to find out. What is the temperature of this outgoing humid air, and how many kgs of this cooling water we will get at 35 degrees centigrade. It will be less than 1 kg because some of it will vaporize and become, the air will become more hotter and more humid. All right, solve this problem. You can give some names to these streams. Let's say we call this as stream number 1, we call this as stream number 2, we call this as stream number 3, we call this as stream number 4.
Sir, I tried this problem in the
Hmm.
last year questions. I just got stuck in the last equation.
Okay, fine.
Like, it was 5 kgs of water there,
Uh,
and the amount of water removed I got as 17 kgs.
oh, okay. Try this now. You can use any method you like. You want to do it by your method, that is fine. You want to do it based on the reference temperature and reference state, that is also your choice. If you want to solve it by choosing some reference temperature, it is your choice, totally your choice. You can take any reference temperature. Anybody is solving, not solving? Anybody stuck?
Solving, sir.
Okay. Anybody thinks that we are talking Greek, Latin? Good. Nobody thinks it is Greek, Latin, so people are solving. Anybody stuck? Anybody needs hints? Anybody wants hints? Good. Nobody wants hints. How much more time do you need?
5 minutes, sir.
Okay.
Uh, so again, the bad equation. It's too big.
Any answers so far? Nobody has any answers. Praveen, Mayur.
Sir,
Sir,
the
I got the
equations are
equations, but the calculation part is a bit tough.
Okay, calculation parts are a bit tough. You want to use Excel? You can use Excel. You want to use calculator? You can use calculator.
15 अरे sir 5 more minutes.
sir
Oh,
equations are far too complicated.
Mayur, doesn't matter. You are using a laptop or you are using a mobile or a desktop. What are you using?
Mobile.
Mobile. Do you have a desktop which available readily or a
Yes, sir.
laptop? So open laptop, open Excel and solve using Excel. Use goal seek.
Okay, sir.
How many unknowns do you have, Mayur?
Sir, three unknowns and three equations, but I can convert it into two.
And then 2 to 1 you can convert. कौन सा 3 unknowns, Mayur?
S- Sir, the kgs of cooling water. I mean, the
In
kg
step
of
number 3
water which is,
for
yeah, the
evaporating.
kg. Yes, sir. The kg of water which is evaporated.
Okay, that is one unknown.
The second one is the temperature,
Correct.
and the third one is, sir, partial pressure of uh, of stream number four.
Array, but partial pressure you can write in terms of x, na?
So I got the answer.
Great. Yeah, Arya, great. Wonderful. What is the answer?
Uh, T is equal to 39.76.
Okay, so let's just say 40.
Yes, sir.
And how many kgs?
So I've just found T till now. I'll
Oh, okay.
just tell it to you in a minute.
Okay, okay. So Mayur, if you write the partial pressure in terms of x, then you will have x as one unknown and t as another unknown, two unknowns.
Yes, sir, but exponential form is getting involved.
Correct, correct, correct. So try to see if you can make it into one unknown, that is the only unknown as t.
Okay, sir, I'll try.
Sir, it is a very bad equation.
I know it is very bad because of Antoine equation.
Yes, sir.
So that's why I'm suggesting you can use Excel. Participant.
And sir, kgs of water evaporated is 0.0152. Sir,
Yeah. Yes, I'm listening.
kgs of water evaporated is
Hmm.
0.0152.
Right. So, okay. So we will say um, kgs of water evaporated. So shall we say 15.2 grams?
Yes, sir.
Did you use Excel or did you use calculator?
Graphic calculator.
Ah, okay. So just you're just plotting the left hand side, right hand side as a graph, and then you're seeing point of intersection.
Yes, sir.
Ah, okay. So finally, you converted the two unknowns into one unknown,
Yes, I converted mass in terms of temperature,
temperature.
and,
Yeah, yeah,
and then I got it.
yeah. Yeah, your answer is more or less right. Yeah, I mean, I don't have the exact value, but yeah, more or less it looks okay. Mine is coming something like 44 degrees centigrade and 2.22 grams. But that's okay.
Yes, sir. Yes, sir. I got 44.5 degrees Celsius,
Uh, and
23 gram.
yeah, 22.6. So just a small error, I guess, somewhere. Praveen, any answer?
Sir, calculate.
Mayur, are you trying with Excel?
Yes, sir. Trying.
Okay.
So I'm getting 46 degrees Celsius and 23 grams, sir.
Okay. Arya, just checks. There might be some just small error somewhere.
Yes, sir, I'll do that.
Which method did you use? Did you use your method or did you use the reference condition?
Sir, I used my method, but I think I made a mistake in the calculation of humidity. Maybe there might be a small error over there.
Okay. Nishant, which method did you use?
Sir, I used my method.
You still don't seem to be convinced about the utility of defining a reference and finding out conditions in stream numbers, enthalpies of streams 1, 2, 3, 4, and writing enthalpy in equal to enthalpy out.
Sir, like
That's okay. You need not be convinced. Hopefully, by the end of next week, you will be convinced. Urv, which method did you use?
So I used my method, so I didn't use a reference method.
Ah, okay. So the problem with your methods is that you have to keep track of where each component is going, where water is going, where air is going. You have to keep track and you have to figure out which component is going from what stream to what stream. So imagine a plant where there will be multiple streams, whether it will be a good idea to keep track of your keep whether it will be a good idea to use your method or to use enthalpy in enthalpy out kind of method. Don't worry, I will you will get convinced in the end. It's okay, you can continue using your method. Finally, any method that gets you an answer. Method is not important, concepts are important. As long as you stick to enthalpy calculations properly, should we solve or should we not solve?
So 2 minutes, I'm very close to the answer.
Okay. Any other answer? Anybody else? Anybody would like to volunteer? Ram, would you like to volunteer?
No, sir, I have not reached to the answer yet.
It doesn't matter. Even if you have not reached the answer, that's okay. As long as you have started something and done something, you can volunteer and tell what you have done. No? Yes?
Mm,
Sir, I am getting temperature as 44.56.
Okay, 45.
And water evaporated is 31.7 grams.
So Ram, I take it that you are not interested in volunteering.
Sir, I can volunteer till material balance or energy balance.
Material balance, so it is now your junior stuff. Material balance, so we have done decades ago. Material balance में क्या है? Aditi, would you like to volunteer?
So I'm still trying.
Okay, but would you like to volunteer and tell us what you have tried so far?
So I'll take some time.
Some means how much time? 1 minute, 2 minutes, 5 minutes, 10 minutes, 20 minutes? Quantify. Some is a qualitative word. Bhakti, would you like to try? I don't think you have tried any time. Okay, let's just try to solve with our reference condition kind of thing. So stop whatever you are doing. Stop wherever you have reached. Stop at that point. Don't go forward. Just let us try to solve by this method. Let's say we take a reference. Anybody, what reference would we want here?
30 degrees.
30 degrees centigrade you can take. Let me just take some reference as last time. Let's say 30 degrees centigrade. I can take reference. Let's just say I want to take reference at 0 degrees centigrade. Okay, and I will say dry air has 0 enthalpy. I will say liquid water has 0 enthalpy at this reference temperature. These are the only two components that are there. Air and water, these are the only two components. Air is in the gas state, water is in the liquid state or vapor state. So I have a choice whether I want to take liquid water at 0 enthalpy or water vapor at 0 enthalpy. Let me just, for convenience, let me just say liquid water at 0 enthalpy. So I will just have to add enthalpy wherever there is water vapor. Okay, so let's talk about stream now, material balance, right? So assume material balance. We don't know how much water evaporates. Let's say X kgs of water evaporate. So then from material balance, this number of kgs that are there in stream number 3 would just be 1 minus X. 1 minus X. And kgs of water vapor in the stream number 4 would be the humidity of stream number 3. So at 25 degrees centigrade, at 30 degrees centigrade and a wet bulb temperature of 25 degrees centigrade, we can use the humidity chart because pressure is 760 mmHg. If pressure had been something else, we would not have use the humidity chart and get to the humidity, right? So if you use the humidity chart, anybody wants me to explain humidity chart again, or you will know how to calculate using the humidity chart? Somebody say something. You want me to open humidity chart and show you, or you can do it you are comfortable enough in doing it?
We are comfortable.
We'll do it, sir.
Yeah, comfortable. Fine. So this humidity of the incoming air we will know. And now the humidity of the outgoing air would be this H plus X, right? Oh, sorry, I should just say, I should convert not in terms of humidity, I should actually write in terms of kgs of water vapor, right? This we know. So the kgs of water vapor would be the kgs that are coming from stream number 2 plus X, right? So we have written it in terms of unknown X, and temperature, let's say, is T degrees centigrade. That's also an unknown. So let's calculate enthalpies. Enthalpy of stream 1. It is 1 kg into Cp of liquid water into 50 minus 0. It is at 50 degrees centigrade. We are finding enthalpy with respect to this reference condition, 0 degrees centigrade, liquid water having 0 enthalpy, right? Cp of liquid water is, let's say, 1 in terms of kilocalories. So kilocalories per kg Kelvin. This is Kelvin, this is kgs. So this is in terms of so many kilocalories. So many, we don't have to worry about so many. It is actually a number we know, 50 kilocalories. Okay. Enthalpy of stream 3. Stream 3 has liquid water. It has 1 minus x kgs of liquid water, Cp of liquid water, and it is at a temperature of 35 degrees centigrade. With respect to the reference, it is 35 into 1 minus x kilocalories. Okay. Enthalpy of stream 2. Somebody tell me, actually kg is actually humidity here.
So 0.018,
0.
which is because of 0.5 kg air becomes 0.009.
Right. So it is 0.018 kgs of water vapor per kg of dry air. So the kgs of water vapor would be 0.009 kgs. Okay. Thank you. All right. And then the kgs of water vapor in stream number 4 would be 0.009 plus x kgs. Okay. So now enthalpy of stream 2. What does stream 2 contain? 0.5 kg of dry air and 0.009 kg of water vapor. But my reference is liquid water at 0 degrees centigrade having 0 enthalpy. So 0.5 kgs of dry air, so that will be 0.5 of dry air, 0.24. It is at a temperature of 30 degrees, 30 minus 0 reference. So in terms of enthalpy versus temperature, if we think about 0 degrees centigrade, 0 enthalpy, this is liquid water. We have now water in the vapor state at 30 degrees centigrade in stream number 2. Right. So again, going from here to here, we can go by different paths. We can go by this path, red path, heat, vaporize liquid water and heat up water vapor at 0 degrees centigrade, or heat up liquid water and then vaporize at 30 degrees centigrade. Right. So let's just take, let's say, route 1, route 2. Let me just take route 2 in this particular case. Just any route is okay. I just take route root 2 for this. So 0.009 kgs liquid water is to be heated, Cp of liquid water from 0 to 30. That's our actual temperature at which water vapor I have, plus 0.009 kgs into lambda at 30 degrees centigrade. Okay, root 2. Had I taken root 1, this would have been 0.009 kgs into latent heat at 0 degrees centigrade plus 0.009 kgs into Cp of water vapor into 30 minus 0. Right? You will see that you will get the same answer. So this is from root 1. Sorry, this is root 2 and this is root 1. Right? We just want any one root. Let me just take a root 2 for convenience. At this, not convenience, it's just some root I have to choose. Okay, so that's enthalpy of stream number 2. Let's look at stream number 4. Stream number 4, temperature is T degrees centigrade. What does stream number 4 contain? Stream number 4 has 0.5 kgs of dry air and it has 0.009 plus X kgs of water vapor at T degrees centigrade, and it is 100% saturated. Right? Do you agree with that? So enthalpy of stream number 4, it is enthalpy of this. So enthalpy of 0.5 kgs of dry air, it is 0.5 into Cp of dry air 0.24 kilocalories per kg into T minus 0. That's our reference that we have taken. That's the reference that we have taken, 0 degrees centigrade. Now enthalpy of 0.009 plus X kgs of water in the vapor state at T degrees centigrade. So now it is at T degrees centigrade. Okay. So again, root 1 or root 2, we can take any root. Let me take, I had taken root 2 in the earlier case. So this should be lambda. Now let me take root 1. I just so that everybody knows how to do it by different ways. So what is the enthalpy associated with this 0.009 plus X kgs of water vapor by root 1? Okay, I'm vaporizing it first, 0.009 plus X into lambda at 0 degrees centigrade. Plus now I have to heat up water vapor 0.009 plus X kgs into Cp of water vapor 0.45 kilocalories per kg Kelvin into T minus 0. So this is using root 1. This was using root 2. Okay, I can choose any root I want. It doesn't have to be the same, because any way we do, we would still get the same enthalpy. Enthalpy is a state function. Okay, so now I can write enthalpy balance. Enthalpy coming in from stream 1 plus enthalpy coming in. Stream number 1 is bringing enthalpy. This is our control volume. Stream number 1 is bringing enthalpy. Enthalpy in from stream number 2 must be equal to enthalpy out from stream number 3 and enthalpy out from stream number 4. I am not supplying any additional enthalpy from outside. I am also assuming that there is no loss of heat to the surroundings, right? As if it is very nicely insulated. No loss of heat to the surroundings or no additional heat being supplied from outside. Okay, so enthalpy from stream number 1, that's 50. Enthalpy in stream number 2, coming in from stream number 2, that is this value. Right, not 0, it is just this whole value. Enthalpy in stream number 3, 35 into 1 minus x. Enthalpy in stream number 4, it is this value. Right. So I have two unknowns now. One, so this one equation is from enthalpy balance. Two unknowns, t and x. But are t and x related? Isn't it? What do I know about stream number 4? Stream number 4 has 100% RH. Right? Do you agree? So if I say T degrees centigrade, I can find out vapor pressure at T degrees centigrade. Okay. Antoine equation. Humidity would be vapor pressure divided by 760 minus vapor pressure into 18 divided by 28.84 kgs of water vapor per kg of dry air. And then I can write in terms of x, because total kgs of water vapor is 0.009 plus x and kgs of dry air is 0.5. So this must be equal to 0.009 x, 0.009 plus x, that is kgs of water vapor in stream number 4 divided by kgs of dry air. Do you agree with that? One way to do is to just do trial and error. So assume temperature. What temperature will you assume? Obviously, it has to be more than 30 degrees centigrade and it has to be less than 50 degrees centigrade, isn't it? It has to be somewhere in between 30, because air is going to get hotter, but it cannot get as hot as the hot water, nor can it be more than the hot water, because hot water is what is giving up heat. Do you agree with that? Yes, no?
Yes, sir.
Right?
Yes, sir.
Yes, sir.
Right. So suppose I assume that the temperature is 40 degrees centigrade. Okay. Now I can calculate vapor pressure at 40 degrees centigrade. I can calculate, because it is 100% RH, vapor pressure and partial pressure must be the same. Then I can calculate humidity at 40 degrees centigrade, at 40 degrees centigrade, 100% RH, and then I can calculate what would be this value of x. Right? Now I have got 40 degrees centigrade. Now I have got x. I can get the enthalpy of stream number 4 as well. I can now check whether LHS of enthalpy balance equation and RHS of enthalpy balance equation. It is finally one nonlinear algebraic equation to be solved. Isn't it? So if I get this equal enthalpy of RHS and LHS and RHS, if they're equal, that means my assumption was correct. But if they're not equal, maybe I will assume. Next guess. Temperature is, let's say, 45 degrees centigrade. I will find out vapor pressure at 45 degrees centigrade. I will calculate x, because stream number 4 is 100% saturated. Now I will put in the energy balance, find out the enthalpy of stream number 4. I will check the LHS and RHS. LHS is enthalpy coming in, RHS is enthalpy going out. Check if they are matching with each other. If not, I will find out which is larger, LHS is larger or RHS is larger. I will find out here which is larger, LHS is larger or RHS is larger. Then I will decide whether I want to go below 45 or I will go above 45. Right? So if you do it only once or twice, you will get an answer very quickly. Or use any of your softwares, Excel or your calculator, anything that you like. Choice is yours. Mayur, did you try to get the answer for using Excel?
Yes, sir. I got temperature as 47.61 degrees Celsius.
47, that's way too high.
Yes, sir. I got.
But just check what you have typed in your Excel.
Yes, sir.
Okay. So now, do you think this method is better than your method? Yes, no, somebody say something.
Yes, sir. This was better.
Or you may still say that no, I find my method better because it is more convenient to me. It's like I like red color. That's okay. I like vanilla ice cream. Or I don't like vanilla ice cream. I like butterscotch better. Right? It's up to you. Okay. Slowly, I'm trying to get you to use this method, but it's okay. Okay, can we go to the next problem?
Yes, sir.
Any other doubt? Ram, are you comfortable?
Yes, sir.
Will you be not comfortable in the sense comfortably sitting? Are you comfortable with solving the problem?
Yes, sir. Yes, sir.
Okay, let's go to the next problem. Anybody uses salt at home?
Yes, sir.
Ah, very nice.
Yes, sir.
What is the cost of that salt?
₹16 per kg.
Yes, sir.
Sir, 21.
71?
20 rupees.
70, 70, 70.
21.
21, I thought 71 you are saying. Okay, so let's say cost of salt is, let's say, 20 rupees. Okay, how do you make salt?
Evaporating of salty water.
Salt water.
Salt water comes from where?
Seawater.
Sea.
Seawater, right. So let's assume that we have something called as an evaporator. We have used evaporator earlier. We didn't see how it looked like, but now we are going to see how it looks like. So let's say we put in salt water, seawater. Let's say this seawater contains 3 weight% sodium chloride. Okay. Let's say we want to concentrate it to 50 weight% sodium chloride, and we want to evaporate the water. Right? Do you agree? Let's say seawater is at 30 degrees centigrade. We supply it to an evaporator. We evaporate the water vapor. We have done material balance calculations, right? Do you remember material balance calculations?
Yes, sir.
Yes, right. So if I take 100 kgs of seawater, that will have NaCl and water. It is weight percent is 3 and water is 97. So if I take in terms of kgs, I will have 3 kgs and 97 kgs if I take basis as 100 kgs of salt water, seawater, right? Sodium chloride 50% we want. So this stream will contain NaCl, it will contain water. In terms of kgs, if I write all the NaCl is going to come here 3 kgs and it is 50% by weight, therefore water also must be 3 kgs, and therefore the amount of water evaporated would be 97 minus 3, it would be 94 kgs, right? Material balance straightforward. Now it seems like child's play. Even your younger sibling could do this, in even if the sibling was in, say, 3rd standard, 4th standard, 5th standard. Just taking some names. Now I have to supply energy to evaporate water. Yes, no? Yes or no? We need to supply energy or not?
Yes, sir.
Yes, sir.
Now, so what we will do is we will take another bigger vessel, put that bigger vessel outside this evaporator vessel, right? Or put the evaporator inside your bigger vessel, just like you were cooling Maggie. Who was cooling Maggie by putting it in another vessel? Somebody was cooling, right? Maggie.
Ansh.
Sir, I cool the milk like that. Maggie.
You cool the milk like that, not Maggie. So you are a good boy. You don't drink, you don't eat Maggie. You are a good boy. You drink milk. Fine. Okay, so we need to supply heat. So this is something, it is called as a jacket. As if this vessel is wearing a jacket. You have seen a person wearing a jacket. Person wears a shirt and then on top of that wears a jacket. Right? So it's just like that. We are having a jacket outside this evaporator vessel. Okay. Can you tell me, let's say total pressure is 760 mmHg. Can you tell me what would be the boiling point of this solution? This solution, there is an agitator, and we are saying this solution, important concept coming up, this solution in the evaporator is well mixed. Well mixed in the sense that as soon as you supply this 100 kgs, or we can say kg per hour, we want continuous process, that as soon as this initial or the inlet comes in, it is all nicely well mixed. So well mixed that concentration everywhere is the same, temperature everywhere is the same. What is the meaning of well mixed? Concentration and temperature everywhere inside is the same. What will be the value of concentration?
Sir, in what terms do you want the concentration?
Weight percent of NaCl. What would be the weight percent of NaCl inside? Can you visualize?
No, sir, I didn't get your question, sir.
I am saying that we are supplying 3 weight percent sodium chloride. It is coming in at 100 kg per hour.
Yes, sir.
It is getting evaporated. The concentrated sodium chloride is going out at high temperature and it is having a 50 weight percent concentration. It is having 50 weight percent concentration. I'm saying the evaporator solution inside is well mixed, meaning the concentration of sodium chloride inside the evaporator and temperature inside the evaporator is the same everywhere. Now, what will be the value of concentration inside? Can you tell me?
It will keep changing as the temperature keeps,
Well mixed.
as the amount of water keeps
No, it is
changing.
steady state. Steady state means 100 kg per hour is coming in all the time. 50 kg or whatever this solution, 50% solution is going out all the time. Water vapor is going out all the time. steady state. So concentration, temperature everywhere is not change with time, and because it is well mixed, concentration and temperature everywhere inside is the same. Let's say, for example, Ansh is using this hot milk is being cooled, but Ansh is stirring so vigorously that temperature, if I look at anywhere inside the milk cup, it is the same everywhere. That is the meaning of well mixed. Only thing is that in Ansh's case, it is reducing all the time with respect to time. But now we are looking at steady state as if somebody is pouring the milk all the time and Ansh is drinking the milk all the time. Ansh, can you visualize?
No, sir, I cannot visualize drinking it.
I will draw a picture for you. So imagine that there is a milk cup. You are stirring it. Your hot milk is coming in at, let's say, 80 degrees centigrade. Now it is too hot for you to drink. So you are having this water outside. You have a straw and you're drinking milk all the time, which is at 40 degrees centigrade. 50 also, it will cause burns. Right? So hot milk is coming in all the time. You're drinking milk all the time at 40 degrees centigrade. Everything is the same. Temperature is the same inside everywhere. And because you are taking the substance out from this vessel, this temperature also must be 40 degrees centigrade all the time. Steady state. Now can you visualize, Ansh?
Yes.
And this water is infinite. Assume that this water is 30 degrees centigrade always. Arya, can you visualize now? Instead of milk, we have salt solution.
So somewhat, but okay.
Because this 50% solution is coming in from inside the evaporator, concentration everywhere must be 50 degrees centigrade, must be 50%. It is well mixed. Concentration everywhere inside is the same. It is equal to the outlet concentration. Not inlet, because as soon as that 3% comes in, it gets mixed. That mixing is so vigorous. Now can you visualize? It's a very, very important chemical engineering concept. We are going to use it again and again and again. Well mixed. That's the concept. Concentration everywhere is the same. It is equal to the outlet concentration. Okay, just think about it. I will give you some time. So this concentration everywhere inside is 50 weight%. That's how that solution is coming out. It is coming out from inside, right? So inside concentration must be equal to 50%. Okay, Arya?
Yes, sir. Okay.
What would be the temperature inside? Can you tell me?
The temperature that is coming out.
Temperature inside as well as temperature at which it is coming out. They are the
Yes,
same
sir.
temperature, right? Because it is well mixed.
Yes, sir.
What do you think will be temperature? What is evaporating?
Water.
Water. So do you think this solution is boiling?
No.
Solution is not boiling. Otherwise, how will water evaporate?
So boiling is temperature specific. Evaporation is not temperature specific.
Okay. Is there any other means of taking out water vapor other than boiling?
No.
So do you think this solution is boiling now?
Yes, sir.
So if it is boiling, what would be the temperature? Anybody can answer? If the solution is boiling, what would be the temperature?
So it is a salt solution. So
Dew point.
So
It would.
it would be higher than 100.
that's all I wanted. Higher than 100, right?
So 117, sir.
अथर्व 117 कहाँ से आया तुम्हारा?
Sir, calculated.
कहाँ से कैलकुलेट किया तुमने?
Sir, 3 kg means rise in temperature, sir. Elevation
Boiling
in
point
boiling point.
elevation. But
Yes, sir,
inside
but
inside it
wouldn't
is
work
50% by weight solution.
Yes, sir.
So 50% by weight तुमने मोलालिटी कैलकुलेट किया
Yes, sir.
एंड मोलालिटी से इबुलोस्कोपिक कांस्टेंट लेके कैलकुलेट किया.
Yes, sir.
अरे वाह, very nice.
Sir, but it doesn't remain that linear.
I know it doesn't remain linear, but that let's assume it is linear just now, right? So assume that ebuloscopic constant or whatever way you want to do boiling point elevation. Let's say for 50% NaCl using molality and all that, ask Atharva if you have any doubts. Let's say boiling point elevation is 17 degrees centigrade. That means at 1 atmosphere, pure water would have boiled at 100 degrees centigrade, but the solution will boil at 117 degrees centigrade. So this is 117 degrees centigrade. This also must be 117 degrees centigrade. And water vapor leaving must also be 117 degrees centigrade. Do you agree with that? It is well mixed. Temperature everywhere inside is the same. And because outlet is from that inside, that outlet and inside anywhere, it must be the same. Concentration and temperature everywhere must be the same, and it must be equal to the outlet. That is the meaning of well mixed. So very, very important chemical engineering concept. You are going to use that concept of well mixed for the rest of your lives. Okay. Now, is the situation clear to everybody? Another 2-3 minutes and we will stop. Let me describe the problem, then you can solve. Okay. Yes, no.
Yes, sir.
Right. So I need to supply heat. To cause this water to evaporate and concentrate the salt solution. Do you agree?
Yes,
or
sir.
no? Somebody say
Yes, sir.
something, Baba.
Yes,
say
sir.
something. Talk. Say something. Otherwise, I don't know whether I'm talking to wall or computer screen or where I'm talking to. Everybody say something. 90 people. Let there be chaos. So, any thoughts on how to supply heat? Anybody know? Has any thoughts on how to supply heat? Nobody has heated up anything at any point of time?
We can use a burner there.
Okay, I will have a fuel and I will have air and I will supply that to a burner. Okay, that's one way. Use burner and
So hot water bath.
burn some fuel. Okay. Second is have a hot water bath. Okay, that is another option. That have hot water outside. Hot water should be at what temperature? Who was saying hot water bath?
So me.
Hardik. So Hardik, what temperature should be this hot water? 40 degrees, 50 degrees, 60 degrees, 70 degrees, 80 degrees.
So hot.
Sir, bare minimum would be 117 degrees.
Correct.
Yes, sir.
Correct.
117.
It has to give heat. This hot water has to be at a temperature greater than 117 degrees centigrade. That means I will have to have this jacket, this hot water at high pressure, right? Otherwise it will be in the water vapor state. Do you agree?
Yes, sir. Yes, sir.
Right.
You
Any
can
other?
rather use an oil bath.
Oil bath, right? Third option is oil bath.
Oil or a sand bath. Sand bath.
Yes, sir. Sand bath.
Okay. Now you will see in third year why sand is not good. It is good for heating peanuts, but not good for heating other things. Sand or oil bath, but it's okay right now. Again, at higher temperature than 117. Any other? Why not use electric heater?
Yes, sir.
Right, I will just put an electric heater inside, immersion heater, and I will connect it to a supply. Will that work?
Yes, sir.
Yeah, correct. I will give you a fifth option. Rather than supplying this hot water, can we supply steam at high pressure and correspondingly high temperature, and then condense that steam? Meaning I will supply steam at high pressure, but at a temperature of, let's say, 137 degrees centigrade. Why 137? I want it to be 20 degrees centigrade higher than this. Okay, I'm just saying I want it 20 degrees centigrade. You can take 10 degrees centigrade higher also, or you can take 1 degree centigrade higher also. Okay, there is some implication of that to how much area I will need, but that will come in third year, so don't worry about it. This steam will condense in the jacket and we will get hot water. This will also be at high pressure and it is at, let's say, 137 degrees centigrade. That means steam is giving only latent heat. Okay, I supply steam at high pressure 137 degrees centigrade. I get hot water at 137 degrees centigrade high pressure. Okay, that I will recycle. I will vaporize it and make it again high pressure steam, and I will supply it again. Okay, is the problem description okay with everybody? Here is what we will need to calculate. Okay, is the problem description okay with everybody? Can I tell you now what to calculate? Yes, no?
Sir, but if we want to collect salt only, so why shouldn't we condense it rather than heating it?
Condense what?
The solution.
The solution, cool, right? Not
Yeah.
condense. We condense vapors, but we cool a solution, right?
Yeah, we can cool a solution.
But till I crystallize out, right?
Yes,
so solubility is much higher than 3%. And solubility doesn't change with temperature much for sodium chloride unless I evaporate.
Understood, sir.
Right? This problem, do you remember?
Yes, yes, yes.
Crystallization, where did that go? Maybe here, yeah. Evaporation. We evaporate something, then we cool something and crystallize. And by evaporation, we make it more concentrated. In that problem, we had made it go from 5% to 30%. Do you agree?
Yes, sir.
Okay, now, so this hot sodium chloride solution now, this we will cool and we will crystallize out sodium chloride. Right? Okay, Aryan?
Yes, sir.
Right. Any other doubt? Can I tell you what is to be calculated?
Yes, sir.
So these properties of steam, I will need enthalpy of steam, right? I will need enthalpy of this hot water. Remember, this water and this steam, it is not mixing with the solution. It is only outside, inside the it is only outside. This whole thing is inside a jacket. That steam is only supplied to the jacket. Steam is not mixing with that inside evaporator. Right? I need properties of steam like enthalpy. And as we go along, we will need other properties, that what is it that pressure, what pressure that I should have so that I will have steam at 137 degrees centigrade. It will condense steam. I want to condense at 137 degrees centigrade and give heat to that water. So I want to know pressure. At what pressure should I supply steam? Should it be 1.5 bar absolute pressure? Should it be 10 bar absolute pressure? Should it be 100 bar absolute pressure? Right? As we go along, we will need other properties like entropy. Not in this semester, but next semester. We will need other properties like Gibbs free energy, which I can get from enthalpy and entropy. Right? We will need other properties like exergy. Don't worry about all these properties. They are all going to come in your semester 3, which we will get from entropy and enthalpy. Okay. So these properties are given for steam. They are given in something called as steam table. Steam tables. Okay. That gives you properties of the steam. I'm going to share 2 videos with you. One about the steam table and one about this particular problem, or maybe 3 videos I will share. Okay, so here is what we need to find. Okay. Find out kg per hour of steam required. Okay. Second is, if we assume that steam is available at rupees 1 per kg. Why rupees 1 per kg? We will talk about that as we go along. But right now, assume that steam is available at 1 rupees per kg. Find out cost of sodium chloride. Even if you say that all these 3 kgs I am able to crystallize out from here. Even if I say all the 3 kgs I am able to crystallize out from here. Okay, and make it into salt. So then cost of NaCl would be cost of steam divided by amount of salt crystals. So cost of steam would be in terms of kg per hour. Amount of salt crystals would be in terms of kg per hour. This would just give you the cost of sodium chloride per kg. Okay. Now, the bigger question is, if this cost is more than 20 rupees, nobody is going to buy salt from you. right? You will go out of business. What should we do to reduce the cost? Okay, so this is one video that I will share with you. This problem is also solved in another video, but don't look at the solution. And once you do this, there is a third video. How do we reduce the cost? Okay, that gives you your next problem. So by Tuesday, watch this video related to steam table. It's a short video. It's only 5 minutes, 10 minutes. Okay, and solve. So that's your homework. Okay, and then Tuesday we will see the solution. We will see the cost, and then that will be our next problem. How to reduce the cost. That will be in another video. Okay, so I'm sharing only one video related to steam table for you because you can solve this problem. All right, shall we stop for the day?
Sir, the boiling point of the solution is coming as 108.
108, not 117.
Yes, sir.
Arre baap re. Atharva, check your calculations. Related
Yes, sir. It is 108.
Arre, 108. Atharva, are you there? You said 117. Okay. Atharva, are you there?
Yes, sir. Yes, sir.
Ebuloscopic constant you took and you calculated 117. Na? Now Praveen and Nishant are saying it is not 117, it is 108.
I will check calculations.
Just check, but it doesn't matter. Whatever is this temperature, whether it is 108 or 117, I want this to be 20 degrees centigrade higher than boiling point of 50% solution. Okay, so Atharva, you can check and you can correct if it is wrong. Praveen, Nishant, you can check, you can correct if yours is wrong. But anyway, take whatever your answer comes of boiling point of 50% water, 50% sodium chloride solution, take 20 degrees centigrade higher than that as the steam temperature. And therefore this also will be at the same temperature. All right. Will you be able to solve? Can you try?
Yes, sir.
Yes. No? Okay.
Yes, sir.
Yes, sir.
Okay. So let's
Yes,
stop
sir.
here for the day. And I will share some videos.